Lesson 3 of the hyperbolics pack is concerned with identities and equations of hyperbolic functions. You get some of these on the formula sheet. So some of these here should look familiar to you as they look like trig identities, but slightly different. Okay, so the top one looks like cos squared plus sine squared equals 1, but notice it's cos squared minus sine squared. So the order does matter for this one. The sine 2x one looks the same as the sine 2x one, so 2 sine x cos x. And again, notice the different sign on the cos 2x one, you get cos squared x plus sine squared x. When in trig, it's cos squared x minus sine squared. So let's prove the first one using our exponential definitions of cos and sine. So looking at the left-hand side of this identity, we know cos x is e to the x plus e to the minus x over 2. I'm going to square that. We know sine x is e to the x minus e to the minus x over 2. I'm going to square that as well. Expanding this out gives me e to the 2x. E to the x times e to the minus x will just give you 1, and you'll get that twice. And you'll get e to the minus 2x, and this will all be over 4. And then on the top of the other one, you get e to the 2x. E to the 2x. Minus 2 this time, because you've got e to the x times e to the minus x gives you 1, will be negative, and plus e to the minus 2x again. And again, this is all over 4. Combining this into a single fraction, because they're both over 4, the e to the 2x and the e to the 2x will cancel out. The e to the minus 2x minus the e to the minus 2x will cancel out. You've got 2 minus minus 2 on the top, which gives you 4 over 4, which just gives you the 1 as required. This similarly works for the addition formulae as well. Again, notice the different signs on this one because the plus or minus is the same way around. So proving the top one. So if we start off with the right-hand side this time, we're going to put in our definition for sine A, which is e to the A minus e to the minus A over 2. Cos A is e to the B plus e to the minus B over 2. And that's plus e to the A plus e to the minus A over 2 times e to the B minus e to the minus B over 2. Just using those definitions for cos and sine. Let's expand these and simplify them. So e to the A times e to the B using e to the A plus B, sorry. Adding those powers. E to the A times e to the minus B gives me e to the A minus B. And I'll get minus e to the minus A plus B. Let's put B minus A actually. From doing these two. And finally, minus e to the minus A plus B. I'll write that as. This is all over 2 times 2, which is 4. Doing the same for the other pair, so I'll get plus e to the A plus B, minus e to the A minus B, plus e to the B minus A, and then minus e to the minus A plus B from the last pair. All of some of this stuff will cancel out. So you've got e to the A minus B minus e to the A minus B. You've got minus this one and plus this one, which will cancel. And then combine this together, you get 2 lots of e to the A plus B, minus 2 lots of e to the minus A plus B, all over 4. Obviously, you can cancel a factor of 2 to give you e to the A plus B minus e to the minus A plus B over 2, which should look familiar to you as the form of sine. So this is sine of whatever's in the power, which is A plus B, again, as required. We also do this for double angle formulae. So again, I'm going to start on the right-hand side because I think it's going to be easier to simplify that. On the right-hand side, I've got 1 plus 2, and then sine A is e to the A minus e to the minus A over 2 squared. So we've got 1 plus 2 times e to the 2a minus 2 plus e to the minus 2a when we expand that out. It's all over 4. The 2 and the 4 will cancel. And if I write this 1 as 2 over 2, also this 2 and this minus 2 will cancel here. So you are left with e to the 2a plus e to the minus 2a over 2, which should look familiar to you as cosh. And whatever's in the power is 2a, so that's cosh of 2a. Now, we mentioned earlier how hyperbolic identities look very similar to trig identities, but sometimes they've got opposite signs in them. This follows something called Osborne's rule. So Osborne's rule says you can work out all the identities for hyperbolic functions from trig identities by taking your original trig identity, and when there is a product of signs, that changes the sign. So it makes positive a negative and negative a positive. So for example, when you've got sine times sine, like you have in the addition formula here for cos, that's why the sign's changed to a plus or minus instead of a minus plus. That's why in this one, instead of being cos squared plus sine squared, it's cos squared minus sine squared, because you've got a product of sines minus sine squared, and same thing for this one. That also translates into tan as well, because obviously tan has got sine on the top. So when you've got product of tans, that changes the sign as well. Or if you've got tan times a sine, that would change it as well. So this allows us to write down some hyperbolic identities corresponding to the trig ones that we know. So for cos 2a, we can write that as cosh 2a equals 2 cosh squared a minus 1. Nothing changes here because there's no sign in it. It's all in terms of cos, so we just add a h into it. For tan, so tan a minus b. On the top of this, there's no product of tans or sines, so that stays the same. But the sign on the bottom is going to change, because on the bottom of this, we have a product of tan. So that plus changes to a minus. We can use identities to come up with exact values and stuff as well. So for cosh x, we know sin x is 3 over 4. Well, we know cosh squared x minus sin squared x equal to 1. So if we substitute that into there, minus it across, so that'll give us cosh x is 1 minus 9 over 16, which is 7 over 16. And then we can square root but we know that, sorry, cosh, not cosh squared. We know that cosh has to be bigger than 0. If you think about the graph of cosh, in fact, it's bigger than 1. Like that. So that tells me the exact value of cosh is root 7 over 4. For tan then, well, we know tan x is sin x over cosh x. Sin x is 3 over 4. Cosh x we said is root 7 over 4. So you get 3 over root 7 for this one, or 3 root 7 over 7. Finding the double angle identity for sin 2x, that's 2 sin x cosh x is exactly the same as for trig, and it's on your formula sheet. Pop in your values for sin x, which is 3 over 4, and your value for cosh x, which is root 7 over 4. And that will give us 3 root 7 over x, the 2 and the 16 cancel. gives us more methods for solving hyperbolic equations. So far we've seen how to solve them using exponential definitions. Now we're going to solve them using identities and discrete quadratics and things. An important point to make is that when you're solving equations involving cosh, you will usually get a second solution. Obviously, your inverse function only gives you one solution because the inverse has to be 1 to 1. But from the original cosh graph, because it looks like this, you should usually have two solutions. This can either be found by just changing the sign using the symmetry graph, or it's actually true that if you change the sign in the middle of the ln, you'll get the same thing. But it's easy to just put plus or minus your answer. For this first one, looks like a disguised quadratic, except we need to change cosh squared into sine squared. So from the formula, which is on the formula sheet, you know that cosh squared x is 1 plus sine squared x. Opposite sign to usual. Usually it's 1 minus sine squared x, but it's changed because of Osborne's rule. Substitute that in, and now we've got a disguised quadratic in terms of sine. I do this up, extend it out. So 2 sine squared x minus 5 sine x plus 2, and if we minus the 5 across, that gives you minus 3 equals 0. This is then quadratic that you can solve on your calculator. I'll factorize it, it's up to you. Gives us two solutions. We get sine x equals 3. Or we get sine x equals minus half, both of which are fine for sine x, because if you remember the graph of sine x goes like this, so we can have both of those, it's fine. Then using the definitions for r sine, we can get r sine of 3, and you get these on your formula sheet. So r sine of 3, let's have a look what that is. So we get ln 3 plus root 3 squared plus 1. Gives us ln 3 plus root 10. Or from this one, we get x equals r sine minus a half, and if we substitute that in, that's ln minus a half plus root minus a half squared plus 1, which will give us ln minus a half plus root 5 over 2. Pause the video and have a go at the U try. This one's going to be a disguised quadratic in cosh, so make sure you get those two solutions at the end of this one. So turning this into a disguised quadratic in cosh, turn sine squared into cosh squared minus 1. Rearrange this and solve it. You get two solutions. You get cosh equals 4 or cosh equals 1.5, both of which are fine because they're bigger than 1. If they were less than 1, they wouldn't be valid, but bigger than 1 is fine. Substituting those in, the bit on the formula sheet gives you ln 4 plus root 15, but also you can have minus ln 4 plus root 15 from the symmetry of cosh. Similarly, for the other solution, you get ln 3 plus root 5 all over 2, but because of the symmetry of cosh, you can also have minus ln 3 plus root 5 over 2. We're going to use identity again for this one, but this time we want to turn this again into a disguised quadratic in cosh. So we're going to use formula for cosh 2x equals 2 cosh squared x minus 1, the same as the one for trig, because there's no products of signs in here, so it doesn't change. So we get 2 cosh squared x minus 1 minus 5 cosh x plus 4 equals 0. This is a disguised quadratic of cosh, which if we solve, we get two solutions. We get cosh x is 3/2, which is fine. And we get cosh x equals 1, which is also fine. R cosh 3/2, that's ln 3/2 plus root 3/2 squared minus 1. That's going to give you 3 plus root 5. 2. And don't forget, we can have the negative of that because of the symmetry of cosh. Cosh x equals 1 only has one solution. If you think about the graph of cosh, crosses the y-axis at 1. If you substitute 1 into your ln formula, you'll just get 0. Now you get ln1, which is just 0, so it just has that one solution, x equals 0. Please pause the video and have a go at the U-try, and I'll reveal the answer in a minute. This one, there's only one double angle formula for shine that you can use. This gives you an equation which you can factorize out the shine x and get shine x equals 0, which has one solution, x equals 0. Or you can get a solution for cosh, which is cosh x equals 5/4. If you put that into the formula, it turns out you get ln2. Don't forget, you can also have minus ln2 for this one because of the symmetry of cosh. Sorry.